Okay, so in the last video we talked about linear functions. We have this picture, and linear function can be summarized by this equation here. A linear function acting on a linear combination is the linear combination of the linear function evaluations. Notice that here he uses parentheses. Here he's dropped the parentheses, and there's a reason for that. But you should think of LU as L evaluated on the vector U. All right. Now, a good exercise that you can think about is this one here. Prove that a linear function composed with a linear function is a linear function. And I can kind of give you some hints with the proof. Let's see, where is it? Where is it? It's here. All right, so composition of linear functions is linear. So here I'm saying suppose L1 and L2 are compatible linear functions. Let me draw a picture of what I'm doing here. And get my tablet. So here we have L1 and L2. And where's my mouse? Okay. This problem, this is always the problem with this. Okay, here we go. So here I have, I'm going to draw, this is a domain. And here I have L1. And here I have L2. So I'm drawing pictures similar to the picture right here. Right, and similar to this picture. Only I'm doing one after the other one. Now, when I say compatible here, what I mean is that you can do this. That the codomain of L1 is the domain of L2. Okay, so the only way that you can compose two linear functions is if the codomain of the first function is contained in the domain of the second function. So this would be the domain of L1. This would be the domain of L2, which is equal to the codomain of L1. And then here's the codomain of L2. That can be anything. All right. So we have two compatible linear functions. And I want to prove that L2 composed L1 is also a linear function. Now L2 composed L1 means you do L1 first and then L2. You do this one followed by this one. All right, so that's what you want to prove. Now, if you want to see my proof, you can pause this video and look at it. But I offer this as something to think about. I think it's a good exercise. So let's go back here and go to the next step. Okay. So we're going to move on with linear functions. And in fact, we're going to look at linear equations. Now, you know, linear equations are very common in science and math. Many engineering problems can be reduced to a system of linear equations. The system of linear equations is related to a linear function. Okay. System of equations has variables, and the variables may be considered as forming a column vector of unknown inputs. So let me explain that a little bit more later, but I'll just put everything on the table first. The constants in the linear equations may be considered as a column vector of known outputs. And finding a solution to the system of linear equations amounts to finding the inputs that produce the given set of outputs. All right. So he has one example here in the text. So let's go there. We have this example with boxes of fruits. And you have two unknowns, the number of bags of fruit and the number of boxes of fruit, x is number of bags, y is number of boxes. And you want to know how many apples and bananas total come from x bags and y boxes of fruit. So here's the information: 2 apples and 4 bananas each box, 6 apples and 8 bananas in each bag. Okay. So if you know the apples and bananas, you can say number of apples, number of bananas are the outputs, and the x and y are the inputs. Number of bags, number of boxes are the inputs. So you can arrange the inputs in a column vector. You can arrange the outputs also in a column vector. And you can see how that, we'll see how that works later. So that's what we say here. And you can verify that these equations, which express the relationship between bags and boxes of fruit and amount of fruit, give a linear function of this vector. Okay, give a linear function acting on the number of bags, number of boxes. Okay, so how would you do that? Take a scalar multiple of this and show that the number of fruits is a linear function. So if I multiply number of bags and number of boxes by 2, then the amount of fruit is going to be multiplied by 2. That's kind of reasonable. Also, if I have one set of bags and boxes and another set of bags and boxes, and I put them together into a big set of bags and boxes, then the amount of fruit is going to be the total of those two. So that's expressing the additive property. So that's what we have over here. Here we have the amount of fruit, amount of apples, number of oranges expressed as a linear function of number of bags, number of boxes. And we know the outputs. We know how many apples, we know how many oranges. And what we want to do is find the inputs, right? So this is related to a linear function, right? Let's go back to the next point. Next point, linear equations may be expressed in terms of linear combinations of column vectors. Now we're going to look at this a little bit differently from what I've been saying. Here I was saying that x and y is a column vector, but you can actually consider this left-hand side as a combination, as a linear combination of the constant column vectors, as it's shown down here. Right. Here I have this left-hand side. I have 2, 4, that's a vector. The 2, 4 multiplies x. The 6, 8 multiplies y. So in fact, I can think of this left-hand side as a linear combination of the two column vectors, where x and y are the coefficients in the linear combination. Okay, so these are the outputs. So what we're going to do is we're going to relate these two ideas. I said previously that the number of apples and oranges is a linear function of x and y. And here I've expressed that linear function as a linear combination using the coefficients x and y. So I'm going to define this symbol here, and we'll see why we define it this way, as expressing the linear function of the vector x and y that in this case produces 20 and 28. Okay, so this is the linear function of x and y that gives me the amount of fruit. And this is defined as this particular linear combination of the two columns in this table of numbers. This table of numbers, as you may know, is called a matrix. We'll be using that word quite a bit. Okay, so let me say that again. We're defining this symbol to be associated with the linear function that expresses the outputs, number of fruit, number of apples, number of oranges, in terms of the unknowns x and y, where x and y are number of boxes, number of bags. Okay. So if you're thinking about this in terms of matrix vector multiplication, you can see that this symbolism suggests that you're multiplying something by something. This is a definition of how you multiply a matrix by a vector. And what you do is you take the matrix, take the columns one by one, and the coefficients of each column are the entries in the vector that are multiplying it. Okay, so you can think of that as 2, 4 is the first column here. 2, 4 multiplies the x. 6, 8 multiplies the y. And we can say this is the definition of matrix vector multiplication. Okay, that's the rule. That's how you define the rule. Now, you may not know another rule for matrix vector multiplication, but if you think about it, it amounts to the same thing. Right? So here we're doing the same thing. Here we have a matrix, table of numbers, and here we have a vector of unknowns, and we're defining this symbol to mean, well, take these columns one by one and multiply them by the associated variable. First column, multiply by first variable. Second column, multiply second variable, etc. Add the results together, and that's how you define this matrix vector multiplication. Okay? So that's how you would find this output from this input. We're expressing the function as this matrix. All right. So here, as the point they make is that you've now organized the information in the problem to express it in a nice way. Okay. This is a nice, convenient way to express all the information in the problem. From this, I can reconstruct the original set of equations because I know how this is defined. Now, because the outputs of this particular function, this is a general 2 by 2 matrix function acting on this column vector xy. And we know from the definition that this linear function can be expressed as a linear combination of the columns of your matrix that you have here. So we call the set of outputs, the set of possible outputs is called the column space because it's a linear combination of the columns of this matrix. So that's a denotation that we'll come back to later It's one of the important spaces in linear algebra. So you may know that vectors belong in vector spaces. The vector space is the set of all possible vectors. And there's a reason why you call it space, because it is similar to three-dimensional space. But we'll get there eventually. Right. So I invite you to watch this video. It gives a good application of how you use matrices to organize data, and actually has something to do with data compression. So that's a very nice video. Now here what he's doing is he's proving what I mentioned previously, that in fact this function does express a linear function of the inputs x and y. Here he's seeing that the function matrix multiply times lambda times a vector is lambda times the matrix multiply. And here we're showing that matrix multiply on the sum is the sum of the matrix multiply. So that's verifying that this is a linear function. Okay. All right. So in summary, in this section, we started with a equation, a set of linear equations, and we reduced it to this kind of matrix form right here. So in fact, any system of linear equations can be reduced to this matrix vector form. So that's really the important point of this chapter. I think that he summarizes it here. He says that. And this type of equation is called a matrix equation or a matrix vector equation. All right. So chapter 2 is all about how you solve this type of equation. All right, so let's stop here, and we'll deal with the rest of this chapter in the next video.